Okay. So we're going to be looking at reactance and impedance.
Okay, sir.
So that's what we want to start with. So can I have the question you're talking about?
Yes, sir. Um. Oh, okay, sir. Sir, I treated some questions the topics we were going to do today. So maybe that's why I could not do it. I was not able to get it.
Okay. So
Mm.
but
Yes, sir.
you've understand the what was it called? The ones we covered in the last class very well, right?
Yes, sir.
All right. So for a quick recap of the last class. So in the last class, we are able to prove some equations, such as the equation for the instantaneous velocity in a generator. So we have that is given as V naught sine omega t, and we have instantaneous current to be I naught sine omega t, and we have that root mean square current, what we can refer to as equivalent equivalent DC current, to be the peak current divided by the square root of 2, and we have that the root mean voltage, what we can refer to as equivalent DC voltage, to be V naught all over root 2, and we have that average power is given as root mean square current multiplied by root mean square voltage, or we have average current to equal to root mean square current square multiplied by resistance. And we said maximum current is given as 2 of the average current, and that's to say that maximum current is equal to the peak current times peak voltage. So these are the equations that we explore in the last class. Am I right?
Yes, sir.
And we are able to explain how we come about each of the equation and the usefulness of each of the equation. So
Yes, sir.
today we want to move forward into reactance and impedance. When I say
Okay, sir.
reactance,
Now, please wait.
okay,
Sorry for cutting you. Sir, I wrote something down on my note. I wrote to get your average power. That's equals to P is equals to I naught times V naught over 2. Is it correct?
yeah, it's correct, because average power is the same thing as 1 over 2 P max. So if P max is I naught V naught, then you're right.
Okay, sir.
All right.
Yes, sir.
so so that was one thing about understanding. When you understand all of these things, you can make your own formula from them. You can make your own, like, it just depends on how much you understand it. Do you understand
Okay,
that?
sir.
So good.
Yes,
Now,
sir.
so in today's class, we want to look at reactance and impedance. What is reactance and what is impedance? Here we want to be talking about circuits now. The reason why we need to
Okay.
understand what we call reactance and impedance is because of the appliances that we use at home. Whenever
Okay.
NEPA generates current for you, when NEPA said, "Oh, we've given you light," though, let me tell you how the process does in just a brief way. Let's take, for instance, that you are staying at OPIC Estate. Are we together?
Yes, sir. You guessed right.
All right. So you stay at OPIC Estate.
Yes, sir.
Let's say this is your house here. You are in your house currently. You see the light that you are
Uh-huh.
using in your house currently. Is either it is the light that they generate from Kanji Dam, or
Okay.
they generate it from other thermal stations in Nigeria. Let's say these are the stations in which they generate those lights. So the light will now, once they generate this light, they will now send this light to a distribution center. That distribution
Okay.
center is at Oshogbo.
Okay.
This distribution center at Oshogbo will now be the one that will now look at, okay, these are the total lights that they generate today, the total power that they generate today. How many percentage will go to Lagos State? How many percentage will go to Abuja? That is the whole of the 32 states that we have in Nigeria. They want to know what will be the portion of each state. They already have what the yardstick that they are using to measure the portion that will go to each state. Am I making sense now?
Yes, sir.
For this example, because I really do not know much about Ogun State, but I will assume that OPK State is in Lagos State.
Okay.
So I assume that OPK State is in Lagos State for better understanding.
Okay.
When Oshogbo want to send lights to Lagos, okay, oh, we've shared this thing. Oh, this is the percentage that is coming to Lagos. Oshogbo will send this to Marina. So when Oshogbo send this to Marina, what will now happen is that Marina will now look at the whole of the local government in Lagos State. So when Marina look at the whole of the local government in Lagos State, will now be like, okay, according to the numbers of I don't know the yardstick they are using to share. Maybe it's according to the money they are collecting from each of the local government, or it is according to the money or according to the numbers of complaints that is in every local government. I don't know their yardstick. Are you getting me now? Because some local government are
Yes.
sharing light, while some are not sharing light.
Okay.
So what's making them share light? I don't know. So, but this is part of what is making them sharing light. Maybe the power is not going to be sufficient to give everybody, so we have to share. Do you understand where I'm coming from now? So
Yes, sir.
Marina will now be like, okay, Agbara people, this is your own portion. So this will send this to Agbara distribution center. So Agbara will now be the one that will now be sharing it bus stop to bus stop, street to street. Are you getting this now? You
Yes,
see,
sir.
during the process of sending this light from one place to another, some of the power have lost.
Okay.
So the exact power that was sent into your house, that is not the okay. For you to get, let's say you receive 1,000 watts. Let's say NEPA send 1,000 watts to your house. Before this, let me say kilowatt, 1,000 kilowatts to your house. Before this 1,000 kilowatts gets to your house, it will have
It
reduced.
will have lost. Okay.
Yeah, so
It
the
will
energy
lost
would have lost
kilowatt.
on the way.
Okay, sir.
So those energy that was lost on the way, the company would look at it that it's not your fault. Are you getting it now? Let's base it.
Yes, sir.
Let's say 980. Let's say 980 kilowatts enters into your house. NEPA will be like, well, it's not your fault. Don't worry, we take care of the 20 kilowatts that get lost. Are you following me now?
Yes, sir.
So if they say they are going to take care of the 20 kilowatts that get lost, that means you'll be paying for what? 980 watts, 80 kilowatt, Abi?
Yes.
But do you know the crazy part of it?
No.
The crazy part of it is that by the time this 980 watts gets into your house, inside the appliance that you are using, there are some materials inside that will not utilize the whole of this power.
Okay.
Maybe your appliance, out of this 980, maybe your appliance is only using 820 kilowatts.
Okay.
Or for better mathematics, let's say your appliance is using 960 kilowatts. 20 kilowatt has lost again.
Yes.
So this 20 kilowatt that lost, you did not use it. But NEPA will charge you for it.
You have to pay for it.
You have to pay for it. You cannot expect them to take care of it again. Are you getting it now?
Mm.
So in
Yes.
order for you not to be paying for what you don't use, or even if you are going to pay for what you don't use, in order for you to be paying in a very minute way, are you getting it? Take for instance that if this thing is 990 kilowatts, you not feel it like you're going to feel 960. Sorry, I'm doing mistake here. This is 980. Let's say this thing is around 975 kilowatts. It's only 5 kilowatts that get lost.
Yes.
You can easily overlook this than overlooking this.
Mm.
Do you understand what I'm explaining there?
Yes, sir.
So in order for you now to be able to be getting amount of current that you are going to use that will be very close to the amount you are paying, that's the reason why you need to understand what they call reactance, what they call impedance.
Okay.
Because if you remember in the last class that we talk about the power that you are being charged for, that I said instead of them to use a peak value to calculate your power, they are now using what?
Yes.
Root mean square.
Mm.
So that root mean square that they are using is the fact that that's the reason why they dash you this 20 kilowatts.
Okay.
Because if they have intentionally used the peak current from day one, this is what you are going to pay for. What lost on the road does not concern them.
Okay.
But because they are being fair, because it's arguable, that's the reason why they are not using this peak current. They are not using what? Root mean square current that makes them to cater for this. So
Okay.
by the time the light plant gets into your house again, there is still a loss. They cannot tell,
Yeah.
no, we don't do business like that. You also have to face your consequence. So in order for you to be able to manage your own consequence very well, you need to understand reactance and impedance. So that will now help us to see how we can maximize the opportunity of reducing loss. Do you understand that
Mm.
now?
Yes, sir.
All right. So if you have understand that now, let us now look at what we refer to as reactance. What is reactance and what is impedance? When I say reactance, what reactance simply means is an opposition. When you
Okay.
want to define resistance, we always define resistance as what? An opposition offered by a conductor to the flow of electricity.
Mm.
So in an AC circuit also, there are oppositions. So the only thing that you know that is always resisting is resistor. Now, let me just use the
Yes.
right word, resistance. You are familiar with resistance very well as an opposition to the flow of current, Abi?
Yes, sir.
But there are other material that also act like a resistance. One of them
Okay.
is capacitor,
Okay.
and another one is inductor. What's different between these
Okay.
three? You see, resistance does not save energy. Resistance does not do
Okay.
what? Save energy.
Say that.
What resistance does is that whatever energy dissipated is converting it to heat straight up.
Okay.
Any energy that it dissipates, resistance is converting it to heat. But
Okay.
capacitor, it stored energy in its own electric field. Are you seeing it now?
Yes, sir.
It stored energy in its electric field. So once you store the energy, it doesn't lose the energy and it doesn't consume it. It only store it. Later, it will release it back.
Mm.
Are you
So.
getting it now? So it's not really consuming
Yes.
energy. The only thing consuming energy right now is resistance. Resistance is consuming energy. But capacitor does not do what? Consume energy, but it stored energy. So Why we said it's not consuming it despite storing it is that later it will still what? Give it back to the. Do you understand where I'm coming from now?
Yes, sir.
The same thing goes to inductor. Inductor also store what? Energy. But his own energy is stored in magnetic
Phone.
field. And there's something we call electromagnetism. For
Yes, sir.
anywhere there is a presence of current, there is what? A magnetic field there. And where you have magnetic field, there is what? Electric field there. That's why we call it what? Electromagnetism. So,
Okay.
for a literal understanding, I'm not really saying that's what it is, but for you to just understand what I just said now, when current is
Mm,
passing through your appliance, are you getting this now?
okay. Yes,
The
sir.
the magnetic field created, the energy in that magnetic field is stored by inductor.
Okay.
The energy created by the what? The electric field is stored by the
The
capacitor.
conductor. Oh, okay.
Is it clear?
Yes, sir.
Fine. So when you now talk about reactance, reactance is the opposition offered by either capacitor or inductor or both of them.
Okay.
Do you understand that now? So when you say what
Yes,
is
sir.
reactance, you just okay, reactance is an opposition offered,
Stored.
the
Okay.
opposition offered by
A
capacitor
capacitor
or
or an
inductor
insulator. Okay.
is inductor, not insulator.
Okay, sir.
Are you getting this explanation like this?
Yes, I'm getting it.
So opposition offered by capacitor or inductor or both of them, because it's possible you have both of them. There are some circuits that they will only contain capacitor, and some circuits will
Mm,
contain only inductor, and some circuits will contain both capacitor and inductor.
okay.
Do you understand that now? So any
Yes, sir.
opposition offered by any of those circuits is what we refer to as reactance.
Yes, sir. Okay, sir.
Clear, Dabi? So you
Yes.
can take this proper definition down now. Take down.
Okay.
Reactance, reactance is defined. Reactance is defined as the opposition offered to the passage or flow. You can use the word flow if you don't want to use the word passage of an
Okay, sir.
AC, because it's not possible for you to have it in a DC. Do you understand where I'm coming from now? Uh-huh. By either inductor, by either the inductor
Or capacitor.
or capacitor. Thank you. Or capacitor or both.
Okay.
Do you understand that now?
Yeah. Yes, sir.
So you might not be hearing some words like inductive reactance or capacitive reactance. What's the difference between the two? When somebody tell you that inductive reactance, what inductive reactance simply means is that the opposition in what? In a circuit that contains only inductor.
Inductor.
So, we say if somebody say define inductive reactance, just come to this formula, this definition, and say inductive reactance is defined as the opposition offered to the passage of an AC by an inductor.
Okay, sir.
So that means that circuit contain only inductor.
Okay.
So if the circuit contain only inductor, that means you are only looking for what? Inductive reactance.
Okay, sir.
Or the circuit can contain both capacitor, both inductor, and the question we say find the inductive reactance. That means you're only looking for the opposition offered by the inductor only. You're not looking for opposition offered by other ones. You're only looking for the opposition offered by the inductor. Am I making sense?
Yes, sir.
Then we have what we call capacitive reactance. Let's say when you say capacitive reactance, what does that mean? It means the opposition offered to the passage of an AC by capacitor. Am I making sense?
Yes, sir.
So that's just it. So both inductive reactance, capacitive reactance, or reactance itself, they are all measured in ohms because they are still opposition.
Okay, sir.
Do you understand that now?
Yes, sir.
Now, if you look at it, you see that we did not talk about resistance.
Yes.
Now, the reason why we don't talk about resistance is that any circuit that contain only resistance, that circuit is said to consume what? Energy. Are you getting it now? And that has been
Yes.
explained by Ohm's law. So there's no point stressing again. But now let us now consider a situation whereby a circuit contain, or let me let you understand. If you look at this, we did not consider resistance, right? Because resistance definitely consume energy. But if you look at those two things we talk about, they don't consume
Okay,
energy.
sir.
Are you getting it now? So that's why we discuss them together.
Yes.
Now, a situation whereby maybe the inductor and resistance, maybe they use inductor and resistance in a circuit now. A circuit that contain inductor
Okay.
and resistance, or a circuit that contain inductor, um, a circuit that contain capacitor and then resistance. Are you following? Or a
Yes, sir.
circuit that contain both inductor, resistance, and capacitor.
Okay.
So any circuit that contain resistance and either inductor or it contain capacitor or their three, the kind of opposition offered by their three or two of them is what they refer to as impedance.
Okay, sir.
Do you understand that now?
Yes, sir.
Reactance is just opposition by either inductor or capacitor or both of them. Impedance is the opposition offered by inductor and resistance or capacitor and resistance or their three.
Okay, sir.
You get it cleared now, right?
Yes, sir.
So when you say impedance, we say impedance is the overall impedance is the overall opposition. Impedance is the overall opposition offered to the passage of an AC mixed circuit containing a
Okay,
resistor
sir.
and or both of an inductor and a capacitor.
Okay, sir.
Do you understand this now?
Yes, sir.
Very, very clear.
Yes, sir.
All right, that's good. Awesome. Now, we now need to start considering all of those circuits one after the other. But before we start considering those circuits one after the other, I want you to know that both both reactance and impedance, they are measured in ohms.
Oh,
So they are resistance.
okay, sir.
Do you get that now?
Yes, sir.
So it can also calculate for reactance. So if you are looking for reactance can also be calculated by the peak voltage of an
Okay.
inductor divided by the peak current of an inductor, or you can say the peak voltage of a capacitor divided by what? The peak current of a capacitor. Do you get that now? Just like
Yes, sir.
resistance is calculated as what? V over I.
Yes.
So that's just that about that. So now let's start by looking at a circuit that contain only resistor. Let's start from that. A circuit that contain only resistor.
Yes.
So subheading AC circuit
Okay.
containing only resistor.
Okay.
So an AC circuit containing only resistor. So let's see how it works. So let's say all right. So this is resistor now. So when you see the symbol, remember it is what? It symbolizes alternate current.
Okay, sir. So I'm not seeing the screen, no.
You're not seeing the screen? Do you mean you didn't see the screen since morning?
Yes, I don't see the screen.
Sorry, oh, I didn't know that I didn't share the screen, oh. You should have talked since. So you're only following my voice since.
Yes.
Sorry, I'm sorry. So can you see the screen now?
Okay, sir. Yes, sir.
So this is resistor, and this is the voltage of the resistor. This is the
Mm,
alternate current, and the
okay.
voltage is the root mean square voltage and the frequency. So why do I put this frequency here is because when you are given a question, you'll be given the voltage of the alternate current, that is DC equivalent voltage of it, and you also be given what? The frequency. Do you understand that now?
Okay.
So this is usually
Yes.
how most of the questions usually being set. You have the voltage, then command the frequency. Am I making sense now?
Yes.
All right. So what do we need to understand here? So let's see some equations that we need to get familiar with whenever we have a circuit that contains only resistance. Are you following now?
Yes, sir.
So let's recall from Ohm's law. from Ohm's law, we have that V is equal to IR. Am I making sense now?
Yes,
So
sir.
if V is equal to IR, we can apply this same thing to an AC circuit because Ohm's law only works with a DC circuit. Are you getting this now?
Okay.
So if we
Yes,
can
sir.
substitute, we have that V, which is this particular V that you are having here, is equivalent to
Yes.
V naught sine omega t. Abi?
Yes.
And this I is equivalent to I naught sine omega t. Am I
Omega
making
T.
sense?
Yes, sir.
Therefore, you have that your resistance R is equal to V over I, isn't it? And
Yes, sir.
that will give us V naught sine omega t divided by I naught sine omega t. So sine omega t will cancel sine omega t, right?
Yes, sir.
Then you have that this resistance is given as what? Peak voltage over peak current. I hope you understand this now.
Yes, sir.
Now, if we recall that peak voltage is equal to root mean square voltage multiplied by root 2. Do you agree with me?
Yes.
And I naught is also root mean square current multiplied by root 2. So we have that resistance can also be given as V root mean square root of 2 divided by R root mean square root of 2, right? So that this and
Yes.
this can cancel. Then we have the resistance to be root mean square resistance versus divided by what? Root mean square current. Do you get that now? So
Yes, sir.
that means we can find the value of our resistance using the peak voltage divided by the peak current, or we use the root mean square voltage divided by what? Root mean square
Root
current.
small current.
Why is it like that? Is because resistance in either way, it will always what? Consume energy. That it will always converted to what? Heat. Do you understand that now?
Yes, sir.
So can I clean this now so that we can look at questions under that? Then we'll move to the next type of cycle.
Yes, sir.
Okay, so let's look at just probably 2 questions under this. I hope you are getting all of these things.
Yes, sir.
Because the essence of trying to derive equations or break equation down for you is for you to be able to remember easily. All right. So
Yes, sir.
this should be example 10. I'm continuing from last class example. So the question says a,
Okay.
a voltage a voltage supply of 12 volts root mean square and frequency frequency 90 hertz is connected to a 4 ohms resistor. It's connected to a 4 ohm resistor. Calculate the peak value of the current. Calculate the peak value of the current. So for us to be able to calculate the peak value of the current, we must know the peak, the root mean square voltage. However, let's see. Let's take for instance that you are in the university right now, because I know you are not taking WAEC again or JAMB. Oh, sorry, this is your last JAMB, by God grace. You are not taking.
Yes.
You are not taking.
Amen.
Yeah, you're not taking WAEC. You're not taking NECO. You're not taking GCA. However,
Yes, sir.
you might want to put your junior ones through, or your street brother, or anybody that comes to meet you for assistance on AC. If they are to tackle this particular question, it is advisable for you to have your full mark that you start with a diagram. Normally, you can solve the question
Okay.
without a diagram. If you are a JAMB bite, if you see this kind of a question in JAMB, you don't need to start drawing any diagram. Do you understand? Because
Okay, sir.
it's a question you can solve without the diagram. But if it is WAEC
Okay, sir.
or NECO or GCE, you have to start with drawing the circuit diagram. So let's draw the circuit diagram. We are told that a voltage supply of 12 volts root mean square and
Root mean.
frequency 90 hertz is connected to a resistor of 4 ohms. So we have root mean square voltage to be 12 volts, and we have frequency to be 90 hertz, and we have resistor to be 4 ohms. Am I right? And
Yes, sir.
and the question say we should look for the peak current. So as Jambite,
Yes.
what do you need to do? All he just needs to do is to recall that R is equals to root mean square voltage
Over.
divided by root mean square current.
Uh, Alright.
Abi?
Yes, sir.
So R is 4, and that equals to voltage, which is 12, divided by what? Current, which is root mean square current. So by the time you cross multiply, you have
Okay.
root mean square current to equal to 12 divided by 4, and that will give us what? 3 ampere. Am I making sense now?
Okay.
Is that the final
Yes,
answer?
sir. Yes, sir.
That's the final answer, right?
Yes. But they say we should look for peak value.
So this is not a peak value, so we need to look for the peak value, right?
Yes, sir.
Good. If it is JAMB objective questions, like JAMB will put 3 ampere to be part of the option.
Yes, sir. You are very correct.
So, and if you accidentally so excited that you've solved and you've gotten 3 ampere, you just pick 3 ampere, and by the time you finish JAMB, you discuss it at home. Oh, I key JAMB, and JAMB don't kill you because
Hmm.
because you solve right, but you didn't pick the right answer because you didn't finish your what? Your solving. So you have to be very, very careful. That's why the fact that it's a 1 minute question does not mean that you should be rushing. You want to be as
Yeah.
relaxed as possible. So it's two things that will make you pass JAMB. One is speed, and two is accuracy. So
Okay, sir.
if you are fast and not accurate, you fail. If you are
Mm.
accurate and you are slow, the same thing will occur. So you need those two things to balance: speed and accuracy.
Okay, sir.
So let's recall that peak current is equals to root 2 times the root mean square current. Am I right?
Yes, sir.
So the peak current is going to be root 2 multiplied by 3. So I have a new calculator. So root 2 multiplied by 3. That will give us the peak current is equal to 4.24 4.243 ampere. So that's the peak current. Do you understand that now?
Eh, no, sir. Sir, wait. From the peak I naught is equals to half root 2 times 3. So we got to I naught is equals to 4.243
Yes, when you use these
ampere.
two to multiply themselves, you have 4.243, and that's your final answer. Is it clear?
Okay, sir. Yes, sir.
So this is how you solve it. If you are a JAMB student, you don't need any diagram. But if you are a WAEC student, you need to start with a diagram. And that's the essence of drawing diagram at the beginning of everything, so that you see what the diagram of a resistor only look like. So for example, if I will sketch this now, I'll have this to be like this. And then I have this, then this. So this is the AC source. So I'll put my 12 volts, then comma, my frequency 90 hertz. I'll put it here. Then here is going to be what? 4 ohms. And I'm done with the diagram.
Okay, sir.
So some people can decide that they don't want to put this one outside. They can put it at the center of the circuit. Are you getting this now? They'll put it there, 12 volts, and then you have 90 hertz. Most of advanced textbooks usually write it like this.
Okay, sir.
I hope it's clear now.
Yes, sir.
So let's look at another example. All right.
Yes, sir.
So for example 2, which is
And then
example 11.
11.
Yeah. Example 11. Calculate calculate sorry please. Calculate the amount calculate the amount of heat. Calculate the amount of heat generated in an external load of resistance 8 ohms if an AC of peak value 5 ampere is passed through it for 100 seconds. Yeah. Okay. So this is what we have right now. How do we calculate
Okay.
for this heat of a thing? So the first thing you want to do is to read. Calculate the amount of heat generated in an external load of resistance 8 ohms. So we are given resistance of the load to be 8 ohms. If an AC of peak value 5 ampere, so that means I naught is what they give us there. Are you seeing the way I'm interpreting it? Is passed through it for
Yes,
100
sir.
seconds.
Sir?
I said, are you seeing the way I'm interpreting it?
Yes, sir.
So we are looking for the amount of heat generated. Sorry. So that's what we are looking for. So the question now is, what is the
Yes,
formula
sir.
for heat in relation to resistance, current, and time? That's how to find formula for anything you want to define. And what they are asking you to look for, you look at the relationship between that thing and the parameters given to you. So if you remember,
Okay, sir.
you have that heat energy, you can use Q to denote it, or H, anyone. You have that heat energy is power multiplied by time. Am I right?
Yes, sir.
If you don't remember, power is equal to work done all over time. Am I
Over
right?
time. Time taken. Yes, sir.
Work done is the same thing as energy. This energy
Yes.
can be heat energy, it can be kinetic energy, it can be potential energy.
Okay.
So if I cross multiply, PT is equals to what? This, right? Then P is
Yes, sir.
power. So what's the formula for power?
Work done over time.
Go and watch. Sorry, please. Go and watch on the screen. Huh? I can't give you my phone if that is what you're looking for. So leave. So power is what? Power is given as
Work done over time.
we know power is work done over time in terms of electricity, in terms of current and resistance. You know, so that you understand very well. It's possible you must have forgotten. Power
Okay.
is given as IV, that's current times voltage.
Okay, sir.
But in this question, there is no voltage, Abby. But we
Yes, sir.
have but we have resistance. So you can still break it down
Mm.
that what's voltage? Voltage is current times resistance. So replace it. You therefore have I square times R. Have you seen that now?
Yes, sir.
I times I, that is I square. So if power is equal to I square R, then I can rewrite this power, this equation for it as H is equal to I square R T. Do you get that now?
Okay.
Now,
Yes, sir.
what you now need to understand is that what type of I is this? Is it peak or it is going to be AC equivalent, DC equivalent I? Which of it is going to be?
Um, it it's going to be peaks. The second one.
What's the second one?
The said peaks. I didn't. So I know you very well.
You know, we have two currents. Whenever you are dealing with AC circuits, you should have in mind that you are dealing with two types of current. You are dealing with a peak current, or even three types of. You are dealing with peak current. You are dealing with root mean square current, which you can call the DC equivalent, and you are also dealing with instantaneous current. So, which of these three is going to be?
If an AC of peak value, we are dealing with peak current.
That's what you are given in the question. You are given peak current in the question, but the actual current to use for you to calculate this supposed to be your root mean square current,
Okay, sir.
because if you look at what the question is stating, the question is all these equations, they are from Ohm's law, and whenever you want to
Yes.
use any equation that are from Ohm's law inside AC, I want you to know that I'm trying to make it so comprehensive so that you can easily remember. Anytime you want to
Okay.
use any equation from Ohm's law inside AC, the right value to use is the root mean square, either voltage or current.
Okay, sir.
Sorry, is it clear?
Yes, sir.
Okay, so if it is clear, we move. H is therefore equal to our I, which is root mean square I, but we don't have root mean square I here. But we know that our peak current divided by root 2 is going to give us what? It's going to give us root mean square I. Am I right?
Yes, sir.
So you have that I naught divided by root 2 all square multiplied by R, which is resistance, that's 8 ohms, then multiply by time, which is 100 seconds. Now, if this time is in minutes or hour, then you have to convert it to seconds before you use it. Am I making sense?
Yes, sir.
So H is equals to, what's our I? That's 5. So we have 5 all over root 2 all square multiplied by 800. Am I making sense?
Yes, sir.
For that reason, this will become what? 25 all over 2 times 800. 2 here 1, 2 here 400. Abi? So 25 times
Yes, sir.
400. 25 times 400. That will give us 10,000.
That's it.
So we have 10,000 joules.
Yes, sir.
So that means the heat converted is going to be 10,000 joules. And you can write it in a standard form, 1.0 times 10 to the power of 4 joules. Or you can write it as 10 kilo joules. Anyone? Do you
Okay,
understand this
sir.
now?
Yes, sir.
Very well.
Yes, sir.
All right. So let's move on to a circuit containing a circuit that contain only inductor.
Sir, please wait. No, don't explain it, though.
Okay. Okay, so write fast.
Okay, sir. Okay, sir, I'm done.
All right. Okay. So want to look at the second type of the circuits now, AC circuits containing only inductor. AC circuit containing only inductor. Now, when you talk about AC circuits containing only inductor, the first one we consider is the one containing only resistor. Okay,
Okay, sir.
so we have this diagram, and we have this. Then this is the voltage of the inductor, and this is you get this now. So this is L for
Yes, sir.
inductor. The L there is for inductor. Now remember that inductor also offered what? Resistance, Abi. So the
Yes, sir.
the resistance offered by the inductor is what we refer to as inductive reactance. So in this formula here, in this equation, what we want to derive right now is how to get the inductive reactance. Do you understand? For this particular circuit. So we're going to start from what we know down to
Mm.
where we don't know, and that's from Ohm's law. So from Ohm's law, we have that V is equal to IR, Abby,
Yes, sir.
where this V is the voltage across the inductor. So you have that the voltage across the inductor is what? VL, equal to the current I that is flowing in the circuit. Then this resistance is going to be what? Inductive reactance. And inductive reactance is written as XL. Am I making sense? I'm substituting into the Ohm's law now, because we have Ohm's law is the foundation for what we are doing. Am I making sense now? So
Yes, sir.
uh I've substituted for what? The inductor voltage, then current, then this is what? The inductive reactance, which is equivalent to what? The resistance offered by the inductor. Are you following now? So,
Yes, sir.
so from here now, I can say, if you look at it from here, you see that um, R is equal to V over I, Abby, which can be peak current
Yes,
and
sir.
then peak voltage. So if you relate it with this, you can have it as inductive reactance is equal to V naught over I naught. Am I making sense now? Or
Yes, sir.
or you can say it is what? V root mean square all over I root mean square. We have proved all of this before, right?
Yes, sir.
Okay. Now, you also have to realize that XL, that is inductive reactance, is the same thing as omega L. Sorry, that was a mistake.